Okay, so what we'll do is we'll start from where we left in the last class. In the last class, we defined what is dimension. Uh, it's basically raised to power of the fundamental quantities. We said that the 7 fundamental quantities are the 7 dimensions of the universe. So, for the example, if we say velocity is meter per second, that is length upon time. So in terms of fundamental quantity, length and time appears in the dimension of velocity, where the dimension in length is 1 and the dimension in time is -1. Then we studied law of homogeneity, that we can only add physical quantities which are same, that means whose dimensions are same. That is, we can add velocity to velocity, force to force, momentum to momentum, but we cannot add two different physical quantities. So if there is any equation, then the law of homogeneity says that only those physical quantities which have same dimensions can be added. But there was no such restriction on the multiplication and the division. We can definitely multiply and divide two different physical quantities having different dimensions. The only constant is that it should result in a uh, physical quantity which makes some sense to us. Okay, and then we said that there are a lot of applications of dimension analysis. So there were some applications which I listed out in the last class. Let us revise those and apply it. The first application is to check the dimensional correctness of a given relationship. Second was to convert unit from one system to the another system. Third is in finding the dimensions of the physical constants or coefficient. And the last as a research tool to derive the new relationship, that is to derive the relation between physical quantity in a physical phenomena. These are few of the applications of dimension analysis. Actually, in engineering, dimensional analysis plays a very huge role when it comes to the simulation and deriving relationships between two new physical quantities and exploiting or exploring physics or astronomy or let's say universe. Okay, so let's now come up to the simple applications, and the first is to check the dimensional correctness of a given relation. So in any correct equation representing the relation between physical quantities, the dimensions of all the terms must be same on both the sides. The dimensions of all the terms must be same on both the sides. Terms separated by plus or minus must be of the same size, must be of the same dimension. That is basically which comes from the law of homogeneity. So for example, in the kinematics equation, S is equal to ut plus half at square, the distance traveled by an object. Okay, S denotes the distance traveled by the object or the displacement of the object when we talk about vectors, regardless of the symbols appearing in the original mathematical relation, whether you have a plus sign here or whether you have a minus sign here. When all the individual dimensions are simplified, for S the dimension is L, we'll simplify the dimension for ut, we'll simplify the dimension of half at square. When all the individual dimensions are simplified, the remaining dimensions must be that of the length. What does this mean? What will be the dimension of S? It will be L. What must be the dimension of ut? Because we're equating this with S, S has the dimension of L, so dimension of ut must also be L. Half is a constant, we don't bother about it. The dimension of at square must be also L. S has the dimension of L. Ut is basically velocity. Velocity is Lt minus 1 and t is time. So dimension is t and it comes out to be L. The dimension of half at square, A is acceleration, and acceleration is the dimension of Lt to the power minus 2. T square will be written as t square. Half is a constant, we'll ignore it, and so it's against the dimension of L. So basically what we see is we have verified this equation as ut plus half at square is dimensionally correct. Okay, so remember there are consistency test, and if an equation fails this consistency test, it is proved wrong. So if we are checking a dimensional correctness of an equation, and if it fails this consistency test, then that equation is 100% wrong. But if it passes, it is not proved to be right. That means, for example, if I write the equation S equal ut plus 1 by 3 at square. Now dimensionally this equation is correct. S is the dimension of L, ut also is a dimension of L, at square also is a dimension of L. So this equation passes the consistency test, but this equation is not right, because we know from our previous knowledge that S is ut plus half at square and not 1 by 3 at square. So what we can say is that the dimensional equation, we have to first pass this consistency test of the dimensional equation. If it is proved wrong, that means the equation is 100% wrong. But even if it passes the consistency test, it doesn't mean it is 100% right. Thus, a dimensionally correct equation need not be actually an exact correct equation, but a dimensionally wrong, incorrect or inconsistent equation must be wrong. For example, if I write S equal to ut square plus half at square, we know that I have messed up here. This is ut square, and if you check the dimension of this term, it will come out to be LT. So this fails the dimensional test, and so we can definitely say, because it doesn't pass the dimensional test, this equation is 100% wrong. Let's take another example to check the dimensional consistency of the equation. I have taken this example from your NCERT book. So we have to check the correctness of this equation from the dimensional point of view. Half mv square is equal to mgh. Remember, if this equation passes the consistency test of the dimensional equation, dimensional analysis, doesn't mean this equation is 100% right. But because we know that this equation is right from our previous knowledge. Okay. So m is the mass of the body, v is its velocity. In the above equation, g is the acceleration due to gravity, and h is the height from which the object falls. So if we take the dimensions of the left hand side half mv square, half is a constant, we can ignore it. M is the mass and v is the velocity, and we know that the dimension of mass is m and velocity is lt minus 1. So I'll write here m lt minus 1 and square. I'll bring the square inside, and this is m L square t to the power minus 2, and I'll further simplify this, and it will be m L to the power 2 t to the power minus 2. So basically what we can say is that for kinetic energy half mv square, the dimension is 1 in m, 2 in L, and minus 2 in t. This is basically the dimension of the kinetic energy. Now let's check the dimensions of the right hand side. M is mass, which will be m. G is acceleration due to gravity, which will be L t to the power minus 2, and h is the length, which will be L. M, L t to the power minus 2, and L. We'll simplify it further. It comes out to m L square t to the power minus 2, which is basically dimension of 1 in m. It has dimension of L 2, and for t it's t to the power minus 2, and we see that the dimensions of the left hand side and the dimensions of the right hand side are exactly same, or we can say that this equation is dimensionally correct equation. Let's move to the next point. To convert unit from one system to the another system. Let's start with a very simple example. If I say the velocity of this car is given to be 18 km per hour, we want it to convert into SI units, that is meter per second. Okay, this is very simple. Everyone knows that 1 kilometer is 1000 meter, and 1 hour is 60 minutes, and each minute is 60 seconds. So 1 hour is 3600 seconds. So what we can do is we can substitute 18 kilometer per hour is equal to 18 kilometer will be represented by 1000 meter, and time r will be represented by 3600 seconds. We'll simplify this, and this will be 5 meter per second. So this was a very simple conversion of velocity from kilometer per hour to meter per second. Let's see how we'll exploit this as a tool of dimension analysis to convert from one system to another. Let's take another example. Let's convert joule into erg. We all know that Joule is a SI unit for energy, and erg is the unit of energy in the CGS system. Okay, and uh, by experience, you know that the dimensional formula for energy is 1 in M, 2 in L, and minus 2 in T, that is M to the power 1, L to the power 2, T to the power minus 2. This is the dimensional formula for energy. Okay, so if I apply the SI unit, then SI unit of mass is kilogram and length is meter, and the CGS unit for mass is gram and length is centimeter. Time is a unit second in both the systems, so we don't have to worry about time. But yes, uh, SI system mass is kg unit, and in the CGS system the unit of mass is gram. In SI system the unit of length is meter, and in the CGS system the unit of length is centimeter. So 1 joule, if I take the dimensional analysis, mass is having a dimension 1, so kilogram, length is having a dimension 2, so meter square, time is having a dimension minus 2, so s to the power minus 2. This is how we represent 1 joule. Now we want to convert this 1 joule into erg, that is CGS system. In CGS system, what we have to do is we have to convert this kilogram into gram, and we have to convert this meter into centimeter. So let's convert it. We'll write 1 kilogram as 1000 gram and 1 meter as 100 centimeter. Now this is square, and you simplify this 3 and 4. So 1 joule is 10 to the power 7 gram per gram centimeter square per second square, and this gram centimeter square per second square will be a CGS unit, which will be denoted as ergs. So 1 joule is 10 to the power 7 ergs. So by example, by taking two examples, I've shown you that how you can use the units of the two systems, and with the help of the dimensions, we can convert it from one system to another system. So let's see what can be the general formula for this. And if I say N1 joule is equal to N2 ergs, then N1, M1, L1 and T1 are the units of mass, length and time in system 1, and M2, L2 and T2 are the units of mass, length and time in the system 2. Then here we have done is 1 kilogram meter square per second square is 1000 gram 100 centimeter square second square. So this is how we can write the formula here, or we can write in general N2 is equal to N1, M1 upon M2, L1 upon L2 square, T1 upon T2 minus square is equal to N1. In CGS and MKS SI system, we know SI system mass is 1 kilogram, CGS 1 gram, SI system length is 1 meter, CGS 1 centimeter, and we substitute this and we get joule is 1 joule is 10 to the power 7 ergs. So now let us try to generalize this formula. Any physical quantity which has dimensions A, B and C in length L, mass M and time T. I am right now talking about only length, mass and time, limiting ourselves to the mechanics part of the physics. But if current is there or temperature is there, we can also take the dimensions of those physical quantities respectively. Okay, and N1 is its numerical value in system 1, in which the fundamental units are L1, M1 and T1, and N2 is its numerical value in another system in which the fundamental units are L2, M2 and T2 respectively. Like in the above example, length, mass and time, the unit in SI system was 1, and the fundamental units of length, mass and time were meter, kilogram and second, and in ergs the unit was 10 to the power 7, and the fundamental units in CGS system for length, mass and time were centimeter, kilogram and time. So we can write this as N2 is N1, M1 upon N2 to the power A, L1 upon L2 to the power B, T1 upon T to the power C. This helps us to easily generalize this formula, where A, B, C are the dimensions of the mass, length and time for a given physical quantity, and M1, L1 and T1 are the fundamental units in system 1, and M2, L2 and T2 are the fundamental units in the system 2. So this is how, with the help of the dimensional analysis, we can easily convert from one system of units to another system of units. Now, another application of the dimensional analysis is to derive the relation between physical quantity in a physical phenomena. See, like this is all very helpful when we try to find out the relationship by experimental means. Okay, and this will only be helpful when the constants which are associated in the equations are dimensionless constant. In only those cases we can use this dimensional analysis to derive the relationship between the physical quantity and a physical phenomena. For example, when we take a simple pendulum, which is basically a simple bob attached to the string, and it oscillates under the action of gravity, and we want to find out what is the time period, that is the time period of the oscillation of the simple pendulum, we can assume that this time period depends upon the length L, mass of the bob m, and the acceleration due to gravity g. If our assumption is correct, then we can use this dimensional analysis to find out how will the time t depend upon the length, mass and acceleration due to gravity. So we assume that the dependence of the time period t on the quantity L, G and M as product may be written as, for example, in L it varies as the power of x, in G it varies as the power of y, and in mass it varies as the power of z. Let me explain you by looking at, like, in the Newton's law of gravitation, when we use the formula F is equal to G m1 m2 upon r square, we said that the force is inversely proportional to the square of the distance between them. So if the distance between the two masses is doubled, the force will become 1/4. So in that it is inversely proportional to the square of r, we say that it's the dimension of r is -2. Okay, so we just said that, okay, it varies as a power of x for length, power of y for g, and power of z for m. We now have to find out the value of x, y and z. Now here this k is simple constant, and we have to be sure that this k will be a dimensionless constant. Otherwise this dimensional analysis technique cannot be used to verify derive this relation. Okay, so where k is a dimensionless constant, x, y, z are the exponents, and by considering the dimensions of both the sides, so if I look at this equation, t is equal to this, the dimension of left hand side, it is t, time, so it has a dimension of 1 in t. If I look at m and l, mass and length, we don't have mass and length on the left hand side, so we can say that in mass and length the dimensions are 0. So the dimensions of the left hand side will be L to the power 0, m to the power 0, t to the power 1. If you look at the dimension of the right hand side, we'll write length as L to the power 1. We'll write length as L to the power 1. G is basically acceleration due to gravity, so we'll write it L to the power 1, t to the power -2, and mass is m, so m to the power 1. So this makes sense to us. Now they are raised to the power x, y and z, so we'll raise this length to the power x, we raise g to the power y, and raise mass to the power z. And what we'll do is we'll try to simplify this. So this will be L to the power x and L to the power y, so L to the power x plus y, mass is m to the power z, and t will be t to the power -2y. Now if we compare the left hand side dimensions with the right hand side dimensions, here length is x to the power of x plus y, and here the power of length is 0. So x plus y is basically equal to 0. Here the power of m is z, here the power of m is 0. So basically z is 0. and here the power of 2y, t is minus 2y, and here the power of t is 1. So what we can see is that x plus y is equal to 0, minus 2y is 1, and z is equal to 0. If we simplify this, we'll get x equal to half, y is equal to minus half, and z is equal to 0. That means the time period doesn't depend upon the mass, it only depends upon L and G as a power of half and minus half. Or we can write T is equal to K square root of L by G, where K is a constant. Remember, this K is a dimensionless constant, and the value of this K, which comes out to be 2 pi, can only be found experimentally. Now, if you want to find the dimensions of the physical constant, for example, F is equal to G m1 m2 upon r square. This equation was discovered by Newton, and in this, G is not a dimensionless constant. G is having a dimension. So, assuming this equation to be correct, now if we rearrange this equation, G is equal to fr square upon m1 m2. Now, if I want to equate the dimensions of the left hand side and right hand side, I'll put all the appropriate dimensions of force, length, and mass in the right hand side and simplify it. We can find that the dimensions of G are m to the minus 1, L cube, and t to the minus 2. So in any equation which is experimentally, when we derive this expression experimentally, and if the dimension comes, the dimension may not be a dimensionless constant, and then we can find the dimensions of that constant by using our equating the equation from the left hand side and right hand side dimensions. So this finishes our this chapter on dimensions, where we have studied the applications of dimensional analysis, and this is very important because JEE Mains and NEET always have one question from the concept of dimensional analysis. Basically, either they ask us to find the dimension or power of any of the physical quantity, or they ask us to convert from one system to another system. So some important points to solve the theoretical questions as the revision. When I say dimension, it's a measure of a physical quantity without numerical values. So it's only giving us that in what dimensions in the physical world this physical quantity have. So for example, if you want to measure the volume of the room, it's basically length into breadth into time. So it has a dimension of 3 lengths in the physical world. If I want to calculate force, which is mass into acceleration, we can say that the dimension is 1 in mass, 1 in length, and minus 2 in t. So it doesn't give us any numerical value, it only gives the measure of a physical quantity. If you want to find out the numerical value, you have to assign a unit to it, a way to assign a number to that dimension. So the dimension of the velocity is length per time, or the unit will be meter per second. So when we say kilometer per hour and meter per second, we'll assign the number to it. We'll say 1 kilometer per hour is 5 by 18 meter per second. So unit is a way to assign the number to that dimension. Dimensionless quantities, and they do not have any dimensions. There are many physical quantities which are dimensionless, and they are basically the ratios between two same physical quantities. So we have dimensionless quantities without units, and we have dimensionless quantities with units. So some examples of the dimensionless quantities without units are strain, refractive index of the medium. Strain is basically the ratio of the two lengths. Refractive index of the medium is basically, you may have studied in your optics chapter in 10th class, refractive index of the medium, which is basically the ratio of the velocity of the light in the two medium. Specific gravity is nothing but the ratio of the density of the two mediums, coefficient of friction, Poisson's ratio, etc. These are all some physical quantities which are dimensionless and they don't have any units. There are physical quantities which are dimensionless but they have units, like plane angle. Plane angle is nothing but a ratio between two lengths, arc length of the circle and the radius of the circle. So it's a dimensionless quantity, but it has a unit radian associated with it. Similarly, solid angle has a unit sterdian associated with it. There are other expressions which you use in the physics, such as sin x, cos x, e to power x, a to power x. log of x, this is basically to the base 10, and ln x log of x, which is basically to the base e, the natural logarithm. These are some of the physical quantities, or these are not the physical quantities, these are some mathematical functions which have no dimensions. And in these quantities, x also has no dimensions. These mathematical functions may be used in some of the physical equations to represent some physical quantities or some physical expression. But remember, these quantities have no dimensions and they are simply ratios. So now, to get the feel of the units and dimensions of different physical quantities, what you have to do is you have to refer the table in the appendix of our study material or of your NCERT book, and that will help you to solve the problems of units and dimensions. With this, our chapter on units and dimensions is over, and in the next class we'll start the first chapter of physics. Basically that will be the first chapter of physics, kinematics or motion in one dimension, and where we will really start enjoying physics. Okay, so the class is over for today.